Imagine standing on a mountaintop where the air is thin and the view stretches endlessly, but something far stranger is happening here, something invisible to the eye. Time itself is ticking faster than it does at sea level, as if the universe has secretly dialed up the speed of reality just for you. This isn't science fiction, it's gravity's quiet masterpiece, a hidden dance between mass and time that shapes everything from the atoms in your body to the fate of galaxies. And the craziest part, you've been living in this warped reality your entire life without even realizing it. Gravity isn't just the force that keeps your feet on the ground, it's the architect of time. Einstein shattered our centuries-old assumptions when he revealed that gravity isn't a pull but a bend in the very fabric of space-time, a cosmic trampoline where planets and stars dent the stage of reality. The heavier the object, the deeper the dent, and the slower time flows around it. Near a black hole, time crawls to a near standstill. On a satellite orbiting Earth, it races ahead just enough that your GPS would fail without constant corrections. Even your head ages slightly faster than your feet, all because gravity's grip is weaker a few feet higher. These aren't quirks, they're clues to a universe far weirder than we ever imagined. So why does any of this matter? Because time isn't some universal metronome ticking the same for everyone. It's fluid, personal, and utterly at the mercy of gravity's whims. This video is your ticket to understanding how the universe really works, from the warped clocks near black holes to the primordial soup of the Big Bang where time itself might have flickered into existence. We'll explore how colliding neutron stars send ripples through time, why dark matter's invisible gravity might be slowing cosmic clocks, and whether time could ever flow backward under the right conditions. By the end, you'll never look at a clock or the sky the same way again. The universe is keeping secrets and gravity holds the key. Let's uncover them together. For centuries, gravity was just the invisible hand that made apples fall and planets orbit, a predictable force obeying Isaac Newton's neat equations. But in 1915, Albert Einstein turned that simplicity on its head. He didn't just tweak the math, he rewrote the story entirely. Gravity, he realized, isn't some standalone force yanking objects through space. Instead, it's the result of something far more profound, the very fabric of the universe bending under the weight of matter. Think of space-time as a giant, stretchy sheet. Place a bowling ball in the center, and the sheet sags, creating a deep well. Now roll a marble near the edge, it spirals inward, not because some unseen force pulls it, but because the slope of the sheet guides its path. That's gravity in Einstein's universe. The bowling ball is a star, the marble a planet caught in its grip. But here's where it gets wild. That warping doesn't just affect space, it warps time too. The heavier the object, the deeper the dent, and the slower clocks tick near it. This revelation didn't just explain orbits, it unraveled cosmic mysteries. Suddenly, black holes made sense, regions where space-time curves so steeply that not even light can escape. The expanding universe clicked into place, with galaxies riding the stretching fabric of reality itself. Even the humble GPS in your phone relies on Einstein's insight, correcting for time's subtle speed shifts between satellites in orbit and receivers on the ground. Yet the true brilliance of general relativity lies in its universality. Whether you're standing on Earth or drifting near a neutron star, the same rules apply. Matter tells space-time how to curve, and space-time tells matter how to move. It's a cosmic tango, with gravity as the dance partner we never knew we had. And every discovery since, from gravitational waves to time dilation, has only deepened the awe for Einstein's masterpiece. a theory that turned gravity from a simple force into the sculptor of time itself. Imagine two identical twins standing side by side on Earth, perfectly in sync with each heartbeat and every shared memory. Now picture one stepping onto a spacecraft bound for the stars while the other stays firmly planted on solid ground. When the traveling twin returns years later, something shocking happens. They've aged less than their Earth-bound sibling, not by days or weeks, but by measurable, undeniable years. This isn't a plot twist from a sci-fi novel. It's the twin paradox, one of Einstein's most mind-bending revelations about how gravity and motion warp time itself. At first glance, it seems like a trick of high-speed travel. After all, Einstein's special relativity already taught us that time slows down for objects moving near light speed. But here's the twist: the paradox isn't just about velocity. The astronaut twin also experiences weaker gravity while zipping through space, far from Earth's heavy grip. That combination, speed plus gravity's absence, makes their clock tick noticeably faster compared to their siblings. Down here, where gravity pulls harder, time literally drags its feet. This effect isn't theoretical speculation. Your smartphone proves it every day. GPS satellites orbit high above Earth, where gravity's hold is slightly weaker. If engineers didn't account for this, your navigation apps would drift off course by nearly 7 miles within just one day. Those satellites are essentially the traveling twin, their atomic clocks pre-corrected to stay in sync with clocks on the ground. Without this adjustment, the entire system would unravel, leaving you lost on backroads instead of smoothly guided to your destination. Dive deeper, and the paradox reveals even stranger layers. If the traveling twin turned around mid-journey to head home, they'd feel a jolt of acceleration, a moment where the rules of physics shift subtly. Some interpretations suggest this acceleration is the key to breaking the symmetry between the twins, resolving what seems like a contradiction. Others argue it's the changing gravitational environment that tips the scales. Either way, the takeaway is clear: time isn't absolute. It's a flexible, personal experience, shaped by where you are and how you're moving. What makes the twin paradox so revolutionary isn't just the math, it's how it forces us to confront our gut instincts about time. We're wired to think of it as a steady river flowing the same for everyone, everywhere. But Einstein showed us it's more like a network of streams, each flowing at its own pace, bending around the gravitational boulders of the universe. From astronauts aging slightly slower on the International Space Station to particles lasting longer in high-altitude labs, these effects are tiny but omnipresent. The universe is playing tricks with time, and gravity holds all the cards. Even in the most ordinary places, your office building, a mountain hike, even the stairs in your home, gravity is quietly tinkering with time. Picture two identical atomic clocks, the most precise timekeepers ever built. Place one at the top of a skyscraper and the other in the basement. Leave them running for a year, then compare. The clock upstairs will be ever so slightly ahead, not by minutes, but by fractions of a second. That tiny difference isn't a glitch. It's proof that Earth's gravity alters time's flow right beneath our feet. The higher you go, the weaker gravity's grip becomes, and the faster time ticks. This effect, called gravitational time dilation, was first measured in the 1970s using atomic clocks aboard airplanes. Flying at high altitudes where gravity is marginally weaker, those clocks gain time compared to their ground-based counterparts, just as Einstein's equations predicted. Today, scientists replicate this with staggering precision. In one famous experiment, researchers placed clocks at different heights in Germany's tallest radio tower. Over just a few dozen meters of elevation, the higher clock ran measurably faster. But here's what's truly wild: you're experiencing this right now. If you've ever worked in a high rise, your head is technically aging faster than your feet by about 90 nanoseconds over a 70-year lifetime. It's an imperceptible difference, but it's real. Even the water flowing through mountain streams experiences time marginally quicker than the ocean's depths. Gravity's influence is so pervasive that no two places on Earth share the exact same time. These discoveries aren't just academic curiosities, they're vital for modern technology. Satellite navigation systems like GPS rely on atomic clocks orbiting 12,000 miles above Earth, where gravity is weaker. If engineers didn't account for time's speed up there, GPS coordinates would drift by nearly 7 miles per day. The same physics that makes mountain clocks tick faster keeps your phone's maps accurate, yet the implications go deeper. These subtle shifts hint at how gravity operates across the cosmos. If Earth's relatively modest mass can bend time, imagine what a neutron star or black hole does. Our planet becomes a living lab, proving that space-time isn't a static stage but a dynamic fabric, warped by every atom. From the peaks of Everest to the Mariana Trench, gravity writes time's rules, and we're just beginning to read them. Black holes are the universe's ultimate enforcers of gravity's dominion over time. Picture an astronaut drifting toward one of these cosmic behemoths, their ship inching closer to the event horizon, the point of no return. To someone watching from a safe distance, something bizarre unfolds. The astronaut's movements slow, then freeze entirely, as if the universe itself has hit pause. Their image stretches and reddens, fading into oblivion while never actually vanishing. Yet for the astronaut, time flows normally. The clock inside their cockpit ticks away seconds as usual, even as the outside universe seems to speed up in a surreal fast-forward. This isn't an illusion, it's gravity's most extreme manipulation of time. The closer you get to a black hole, the steeper spacetime's curvature becomes. At the event horizon, gravity is so intense that not even light can escape its pull, and time effectively grinds to a halt relative to the rest of the cosmos. This phenomenon, called gravitational time dilation, reaches its absolute limit here. A single minute for the astronaut could equate to years, centuries, or even millennia for distant observers. The black hole doesn't just bend time, it fractures it, creating two parallel realities, one where the astronaut plunges inward and another where they remain eternally suspended at the edge. This extreme distortion isn't just theoretical. Astronomers observe it indirectly when studying matter orbiting black holes. Gas and dust spiraling toward the event horizon emit light that appears to slow and stretch, its wavelengths dragged into the infrared like a cosmic echo. Even the supermassive black hole at our galaxy's core, Sagittarius, a star, exhibits this effect. Stars whipping around it at blistering speeds show subtle shifts in their light, revealing how gravity warps time in their vicinity. But the true mind-bender lies in what happens next. Cross the event horizon, and the roles of space and time literally flip. Inside a black hole, the singularity, a point of infinite density, no longer lies in a place but in a time. Falling toward it isn't a matter of moving through space. It's an inevitable march toward a future where the laws of physics as we know them cease to exist. This inversion is why black holes are often called nature's time machines. They don't just slow time, they rewrite the rules, turning it into a one-way street where the past and future collapse into inevitability. Yet for all their destructive reputation, black holes also serve as cosmic laboratories. They magnify gravity's effects to such extremes that they reveal truths about space-time invisible elsewhere. The recent first-ever image of a black hole's shadow, captured by the Event Horizon Telescope, wasn't just a triumph of engineering, it was a direct glimpse into how gravity sculpts the fabric of reality. The dark void at its center isn't empty. It's a prison of warped time where the universe's clockwork breaks down entirely. What makes black holes so fascinating isn't just their power to trap light, but their ability to twist time into knots. They force us to confront questions with no easy answers. If time stops at the horizon, does the astronaut ever truly cross it? Could information about their fate somehow escape, or is it lost forever? These puzzles linger at the edge of known physics, teasing the possibility that black holes aren't just cosmic dead ends, they might be gateways to deeper truths about how gravity, time, and reality itself intertwine. For over a century after Einstein predicted their existence, gravitational waves remained ghostly ripples in theory alone, until one fateful day in September 2015, when the Laser Interferometer Gravitational Wave Observatory, or LIGO, caught the unmistakable signature of two black holes colliding a billion light-years away. The event sent tremors through space-time itself, warping the fabric of reality so profoundly that by the time the waves reached Earth, they stretched and squeezed our planet by less than 1,000th the width of a proton. Yet that infinitesimal wobble contained revolutionary insights about how gravity sculpts time on cosmic scales. These waves aren't like sound or light, they're distortions in spacetime itself, born when massive objects accelerate violently. Imagine dropping a pebble into a pond, but instead of water ripples, the very dimensions of space and time oscillate outward at light speed. When black holes spiral toward collision, their immense gravity whips spacetime into a frenzy, generating waves that carry fingerprints of the cataclysm. Their masses, spin rates, even how time dilated in their final moments. By decoding these signals, scientists essentially perform cosmic archaeology, reconstructing events that unfolded before Earth existed. What makes gravitational waves so groundbreaking is how they reveal gravity's hidden choreography. Traditional telescopes see the universe in light, but black hole mergers emit no light, only these spacetime ripples. LIGO first detection proved not just that gravitational waves exist, but that Einstein was astonishingly precise in his predictions. The black hole's observed behavior matched general relativity's equations to within a fraction of a percent, even as their gravity warped time so severely that a single second near the collision passed much slower than a second far away. Now multiply that discovery by dozens of subsequent detections, neutron stars crashing together, mismatched black holes dancing to their doom, even mysterious objects that might be quark stars. Each event peels back another layer of gravity's secrets. When LIGO caught two neutron stars merging in 2017, telescopes worldwide saw the accompanying gamma-ray burst and kilonova, a gold-forging explosion proving these collisions seed the universe with heavy elements. The gravitational waves arrived first, giving physicists a head start to point their instruments, showcasing how these ripples don't just carry information, they orchestrate multi-messenger astronomy. But perhaps the most tantalizing possibility lies in what gravitational waves might reveal about spacetime's fundamental nature. Some theories suggest that if extra dimensions exist beyond our familiar four, gravitational waves could leak into them, subtly altering the signals we detect. Others propose that quantum gravity effects might imprint on waves from the earliest universe, offering clues to how time itself emerged from the Big Bang's chaos. Future observatories like the space-based LISA mission will hunt for waves from supermassive black holes merging events so powerful they'd warp time across entire galaxies during the collision. Every gravitational wave is a cosmic telegram written in the language of warped space-time. They tell us not just about the objects that made them, but about gravity's ability to bend time like a funhouse mirror. From confirming century-old theories to hinting at physics beyond Einstein, these invisible ripples are rewriting astronomy's playbook one space-time tremor at a time. The early universe was a place where gravity didn't just influence time, it commanded it. Picture the cosmos mere moments after the Big Bang, a seething, ultra-dense soup of energy and particles where the very concept of seconds or minutes would be meaningless. In those extreme conditions, gravity wasn't just one force among many, it was the architect of time's flow, warping its rhythm in ways we can barely fathom. Today, we glimpse this primordial dance by studying the oldest light in existence, the cosmic microwave background, and the faint glow of quasars billions of light years away. These ancient signals are more than distant starlight. They're time capsules carrying imprints of how gravity shaped time when the universe was young. Back then, the cosmos was so compressed that gravity's grip was everywhere, stretching and squeezing space-time itself. Imagine standing in a room where every inch of air is as dense as lead light would struggle to move and time would crawl. Now scale that up to the entire universe. In those first microseconds, particles were packed so tightly that gravity didn't just bend time, it orchestrated it, slowing its passage in ways that would make a black hole seem tame. As the universe expanded and cooled, gravity's hold loosened, and time's flow gradually settled into the steadier rhythm we know today. But the echoes of that early turbulence linger. One of the clearest windows into this era comes from quasars' supermassive black holes at the hearts of young galaxies, shining with unimaginable brightness. Their light, traveling for billions of years to reach us, carries subtle clues about how gravity behaved in the distant past. Astronomers have noticed something peculiar. The light from these ancient objects appears slightly redshifted beyond what cosmic expansion alone can explain. The leading theory, time itself ran slower in those early epochs, stretched by the universe's denser gravitational field. It's as if the cosmos was playing a record on slightly the wrong speed, leaving behind a telltale warp in the music of light. But the real smoking gun lies in the cosmic microwave background, the afterglow of the Big Bang. This faint radiation permeating all of space is like a baby picture of the universe, snapped when it was just 380,000 years old. Tiny fluctuations in its temperature reveal regions where matter was slightly denser, and thus where gravity was stronger. In those spots, time would have ticked more slowly, leaving subtle imprints in the radiation's patterns. By mapping these variations, cosmologists reconstruct how gravity's influence has waned over cosmic history, like tracing the fading ripples of a stone dropped into an expanding pond. What's even wilder is that gravity's early dominance might hold clues to one of physics' biggest mysteries: why time moves forward at all. In the infant universe, gravity's relentless pull caused matter to clump into galaxies and stars, creating the uneven distribution we see today. Some theorists argue this process is what set time's arrow in motion, transforming a featureless early cosmos into the structured universe we inhabit. Without gravity's organizing hand, time might not have a direction, just an eternal, unchanging present. Yet for all we've learned, the early universe remains a frontier. Did time emerge fully formed from the Big Bang, or did it crystallize gradually as gravity's influence grew? Could there have been epochs where time flowed backward, or in loops, before settling into the linear progression we know? Each new observation, from next-generation telescopes to deeper analyses of ancient light, brings us closer to answering these questions. The early universe wasn't just a place where gravity bent time, it was the crucible where time as we know it was forged. And the deeper we look, the more we realize that gravity's grip on time isn't just a feature of the cosmos, it's the very foundation of its history. Neutron stars are nature's most ruthless alchemists' cosmic pressure cookers where gravity crushes matter into forms so extreme they defy imagination. Take a star heavier than our Sun, squeeze it down to the size of Manhattan, and you've got a neutron star. This isn't just compact, it's a realm where the rules of physics as we know them twist into something unrecognizable. A single sugar cube-sized chunk of this material would weigh 1 billion tons on Earth, not because it's magically dense, but because gravity has collapsed the very space between atomic nuclei, merging protons and electrons into a sea of neutrons. The result, a stellar zombie so dense it bends light into tight orbits around its surface and warps time like a cosmic funhouse mirror. Stand on a neutron star's surface. If your atoms could somehow survive the crushing gravity, and time would crawl at half the speed observed from a distance. A clock ticking there for 1 year would show 2 years passing for someone watching from afar. This isn't science fiction. It's gravitational time dilation pushed to the limit, a real-world test of Einstein's theories in conditions no lab could ever replicate. Even the star's magnetic field is ludicrously powerful, quadrillions of times stronger than Earth's, capable of wrenching electrons from atoms light years away. Yet these bizarre objects aren't just cosmic curiosities, they're Rosetta Stones for decoding gravity's secrets. When neutron stars collide, they don't just create fireworks, they send ripples through spacetime itself, detectable as gravitational waves. The 2017 merger observed by LIGO revealed gold and platinum forged in the explosion, proving these events seed the universe with heavy elements. But the real treasure was hidden in the data, precise measurements of how the star's gravity distorted time during their death spiral, offering a stress test for relativity's equations. What makes neutron stars unparalleled labs is how they straddle the line between known physics and mystery. At their cores, matter might dissolve into exotic states, quark-gluon plasma, or perhaps free-floating strange quarks that behave like nothing in our periodic table. Some might even transform into theoretical boson stars, made entirely of particles that ignore the Pauli exclusion principle. These possibilities aren't just academic, they're clues to how gravity behaves at quantum scales, a puzzle that's eluded physicists for decades. Perhaps most astonishing is how we study them. Neutron stars often reveal themselves as pulsars, lighthouses of radiation, beaming across space with metronomic precision. Astronomers use these pulses as cosmic clocks, tracking how their timing shifts when planets orbit them or when they're tugged by gravitational waves. In 2003, the pulsar PSR J0348+0432, a neutron star twice the Sun's mass, provided the most stringent test of general relativity yet. Its gravity slowed time exactly as predicted, even in this extreme regime. Yet for all their ferocity, neutron stars have a surprising soft spot, their surfaces. Models suggest they might be crusted with nuclear pasta, a matter compressed into spaghetti like strands or lasagna-like sheets by competing forces. This bizarre material could crack under stress, triggering starquakes that release bursts of X-rays. It's a reminder that even in these gravity-warped realms, the universe finds ways to surprise us, blending the familiar with the utterly alien. By probing neutron stars, we're not just learning about distant curiosities, we're glimpsing the fate of matter itself under gravity's most tyrannical rule. Every flicker of a pulsar, every gravitational wave from a collision, peels back another layer of spacetime's secrets, revealing how deeply gravity's grip shapes the fabric of reality. And as telescopes grow sharper and detectors more sensitive, these stellar corpses may yet reveal the keys to unifying gravity with quantum mechanics, a breakthrough that could rewrite physics itself. The cosmos is playing a cruel trick on astronomers, one that threatens to upend our understanding of gravity's role in shaping time. For decades, scientists have painstakingly measured the Hubble constant, the number that describes how fast the universe is expanding. But here's the catch: depending on where they look or which method they use, that number keeps changing. Some measurements, like those from nearby supernova, suggest a relatively quick expansion. Others, like readings of ancient cosmic microwave background radiation, point to a slower pace. This discrepancy isn't just a rounding error. It's a full-blown crisis in cosmology, hinting that gravity's influence on time might not be as constant as we thought. At the heart of this mystery lies an epic battle between two invisible titans, gravity and dark energy. Gravity, the sculptor of galaxies and the force that slows cosmic expansion, tugs matter together across billions of years. Dark energy, the enigmatic repulsive force discovered in the late 1990s, does the opposite, pushing space apart and accelerating the universe's growth. The Hubble constant should reflect the balance between these opposing influences over time, but the numbers refuse to agree, leaving physicists to wonder: is our math flawed, or is gravity itself changing as the universe ages? One radical possibility is that dark energy isn't constant but evolves, growing stronger or weaker over cosmic epochs. Imagine a rubber band that starts stretching slowly, then suddenly snaps apart. That's the kind of unpredictable expansion some theories propose. Others suggest gravity might weaken over vast timescales, its grip on spacetime loosening as the universe expands. If true, this would mean Einstein's equations, though brilliant, are incomplete, a local approximation of a deeper, more complex reality. The stakes couldn't be higher. The Hubble constant doesn't just measure today's expansion. It's the key to predicting the universe's ultimate fate. Will gravity eventually prevail, pulling everything back in a big crunch? Or will dark energy rip spacetime apart atom by atom in a big rip? Right now, we're like detectives with conflicting witness statements, unsure whether the cosmos is headed for a slow fade or a violent finale. New tools are rising to the challenge. The James Webb Space Telescope peers deeper into the early universe than ever before, while next-generation observatories like the Vera C. Rubin telescope will map millions of galaxies with unprecedented precision. Each dataset is a piece of the puzzle, helping us untangle whether the Hubble tension is a measurement glitch or evidence of physics beyond Einstein's wildest dreams. One thing's certain: solving this riddle won't just adjust a number in a textbook. It'll redefine how gravity writes time's story across the cosmos. Black holes may dominate our cosmic nightmares, but their theoretical opposites, white holes, offer a twist so bizarre it flips gravity's script entirely. Picture a black hole running in reverse. Instead of trapping everything that crosses its horizon, a white hole violently expels matter and energy, as if the universe itself hit rewind. These hypothetical objects aren't just mathematical curiosities. They're gravity's ultimate rebels, defying time's arrow by turning singularities into cosmic fountains. While no white hole has ever been observed, their possibility emerges straight from Einstein's equations, dangling the tantalizing idea that gravity's grip on time might not be a one-way street. The math behind white holes is as elegant as it is unsettling. In the same way, a black hole's event horizon marks a point of no return for infalling matter. A white hole's horizon would be an exit no object could ever re-enter. Matter would erupt from its core like a geyser, propelled by gravity itself. Some theorists suggest that if you could peer inside a black hole's singularity, ignoring the crushing death awaiting you, you might find it connected to a white hole in another universe, forming an Einstein-Rosen bridge or wormhole. This cosmic tunnel wouldn't just link distant points in space. It could stitch together different moments in time, turning science fiction's wildest time travel dreams into a theoretical possibility. Yet white holes pose a glaring paradox. How could they exist in our universe without violating thermodynamics? Black holes form when massive stars collapse, but white holes would require infinite energy to spontaneously burst into being, ejecting material that was never fed to them. One radical solution proposes that white holes might be black holes from a parallel universe, seen in reverse from our perspective. Imagine two universes branching from the same Big Bang, their timelines mirroring each other like a cosmic Rorschach test. A black hole in one universe would funnel matter toward the singularity, while its twin in the other universe would appear as a white hole, spewing that same matter outward. The implications ripple through physics. If white holes exist, they could explain mysterious cosmic explosions like gamma-ray bursts, events so energetic they defy conventional explanations. Some astronomers have even speculated that the Big Bang itself might have been a primordial white hole, a violent eruption of spacetime from a singularity in some earlier universe. This idea blurs the line between cosmology and metaphysics, suggesting our entire universe could be the other side of a black hole from another reality. But the most mind-bending possibility lies in white holes' relationship to time. General relativity treats time as symmetrical, meaning the equations work just as well running backward as forward. White holes embody this symmetry, hinting that gravity might not care which direction time flows. In a universe with white holes, causality itself could become tangled, with effects preceding causes and the future influencing the past. Wormholes linking black and white holes might create closed time-like curves loops where time circles back on itself, enabling paradox-free time travel in theory, if not in practice. Despite their allure, white holes face steep skepticism. The universe seems to favor entropy and irreversible processes, making their spontaneous appearance unlikely. Yet their theoretical shadow lingers, pushing physicists to ask deeper questions. Is time's arrow truly fundamental, or just an emergent property of our local cosmic environment? Could regions of spacetime exist where gravity flips time's flow like a magnetic pole? Until we detect one, perhaps through an inexplicable burst of particles with no visible source, white holes remain gravity's most provocative what if. A reminder that even the most established laws of physics might hide reversals we've yet to imagine. Einstein's theory of general relativity paints gravity as the smooth curvature of spacetime, bending planets and stars like a trampoline sagging under bowling balls. But zoom into the subatomic world and this elegant picture shatters. Here, quantum mechanics reigns, a realm where particles pop in and out of existence, where time itself becomes fuzzy and uncertain. The problem, these two theories, each wildly successful in their own domains, refuse to speak the same language when it comes to gravity. Reconciling them isn't just academic nitpicking, it's the key to unlocking time's deepest secrets. Take a black hole singularity, a point of infinite density where relativity predicts spacetime breaks down completely. But quantum mechanics abhors infinities, suggesting that at some tiny scale, gravity must behave differently. Maybe spacetime isn't smooth and continuous, but granular, like a digital image pixelated beyond a certain zoom. Or perhaps gravity isn't a fundamental force at all, but an emergent illusion, like temperature arising from the chaos of countless molecules. These ideas aren't just wild speculation, they're the battlegrounds of quantum gravity, the field striving to stitch together the cosmos's biggest and smallest rules. One leading candidate, string theory, proposes that particles aren't dots but vibrating strings, with gravity's quantum version carried by a hypothetical particle called the graviton. Another approach, loop quantum gravity, imagines spacetime as a network of interwoven loops where time itself quantizes into discrete steps like a cosmic stop-motion animation. Both theories predict mind-bending consequences: microscopic black holes that evaporate in a flash, wormholes threading through hidden dimensions, or even the possibility that time doesn't flow at all, but exists as a static block where past, present, and future are equally real. The stakes go beyond theory. If gravity has quantum properties, it could mean that time emerges from something deeper, a process akin to how waves emerge from the ocean's churning, but with no fundamental time beneath the surface. Experiments are already hunting for clues. Ultra-precise atomic clocks can detect if time's flow stutters at tiny scales, while particle colliders search for extra dimensions that might leak gravity's strength. Even gravitational waves might carry fingerprints of quantum spacetime if we learn to read them finely enough. Yet the most tantalizing possibility is that quantum gravity could rewrite our understanding of time's origin. Did time begin with the Big Bang, or was it born from a quantum fluctuation in some timeless void? Could black holes where gravity and quantum effects collide hold the answer? Every unanswered question is a chink in our cosmic armor, a reminder that gravity's grip on time might be far stranger than Einstein ever dreamed. Until we crack this puzzle, the universe's clockwork remains half-hidden, ticking away in a code we've only begun to decipher. Dark matter is the universe's silent puppeteer, pulling strings we can't see but whose effects are everywhere. Picture a galaxy spinning like a whirlpool of stars, except the outer stars move just as fast as those near the center, defying the laws of gravity as we know them. The only explanation, an invisible halo of dark matter, 5 times more abundant than ordinary matter, whose gravity grips the galaxy tight enough to keep stars from flying off into the void. But here's the twist: this hidden scaffolding doesn't just shape space, it bends time itself. The deeper you look, the stranger it gets. When light from distant galaxies passes through dark matter's gravitational field, it doesn't just bend, it slows down, stretched like taffy in a phenomenon called Shapiro time delay. Astronomers have clocked this slowdown in galaxy clusters, where dark matter's gravity acts like molasses on light's journey. That delay isn't just a quirk, it's proof that dark matter's gravitational hand tugs at time's fabric, subtly altering how clocks would tick in its presence. If you could stand in a dark matter cloud, though it would pass through you like a ghost, your watch would run infinitesimally slower than on Earth. Yet the biggest mystery isn't just what dark matter does, but what it is. The leading candidates range from WIMP, weakly interacting massive particles, to actions, hypothetical particles so light they behave more like waves than matter. Some theories even suggest dark matter might interact with itself through unknown forces, creating shadowy structures that mirror galaxies. But here's the kicker: if dark matter behaves differently than ordinary matter, its relationship with time could break Einstein's rules. Imagine pockets of the universe where dark matter's gravity causes time to stutter or warp in ways general relativity can't predict. The hunt for answers is heating up. Deep underground, detectors like Xenon 1T lie in wait for a rare dark matter collision. In space, telescopes like Euclid map its distribution by tracing how its gravity distorts billions of galaxies. Even the Hubble GPS might hold clues. If dark matter's gravity fluctuates, it could leave fingerprints in satellite timing data. Every experiment is a step toward answering the ultimate question: does dark matter's invisible hand also wind the cosmic clock? What's at stake goes beyond astrophysics. If dark matter's gravity influences time differently than ordinary matter, it could mean our universe has layers of time flowing at different rates, hidden streams beneath the surface of reality. Galaxies might not just be embedded in dark matter, they could be floating in time zones we've yet to map. And if we ever learn to harness its secrets, dark matter could become more than a mystery. It might be the key to understanding gravity's full power over time itself. Time crystals sound like something ripped from a sci-fi novel, structures that pulse rhythmically not in space, but in time itself. Unlike ordinary crystals, where atoms arrange in repeating spatial patterns like a diamond's lattice, time crystals break time's symmetry, oscillating between states indefinitely without energy input. It's as if you wound up a clock once and it kept ticking forever, defying the universe's relentless march toward entropy. First theorized in 2012 and created in labs just 5 years later, these bizarre phases of matter aren't just curiosities. They're rewriting our understanding of time's fundamental nature and gravity's role in shaping it. At their core, time crystals exploit quantum weirdness to achieve their perpetual motion. Take a chain of ions chilled to near absolute zero, hit them with precisely tuned laser pulses, and they'll start flipping their quantum states in a predictable, repeating sequence. This isn't driven by energy, the system is already in its lowest possible energy state, but by a quantum quirk called many-body localization, where disorder locks particles into a stable rhythm. The result, a structure that repeats not in meters or millimeters, but in milliseconds or microseconds, like a metronome ticking in the fourth dimension. What makes time crystals revolutionary isn't just their defiance of classical physics, but their potential to bridge gravity's cosmic dominance with quantum mechanics' microscopic chaos. Some theories suggest spacetime itself might have a granular, crystalline structure at the Planck scale, the universe's smallest possible units. If true, time crystals could be tiny windows into this hidden architecture, revealing how gravity emerges from quantum interactions. Imagine zooming in on spacetime until it resolves into a shimmering lattice of interconnected time pixels, each vibrating like a minuscule time crystal. This isn't pure speculation. Experiments are already probing whether gravitational fields affect time crystals' oscillation rates, testing if gravity itself might be an emergent property of deeper quantum processes. The implications ripple across physics. If time crystals can exist in labs, could they also form naturally under extreme gravity, like near neutron stars or black holes? Might the early universe have undergone a phase transition that left remnants of primordial time crystals embedded in spacetime's fabric? Even more tantalizing is the possibility that time crystals could mimic aspects of black hole physics. Just as an event horizon locks information in a frozen shell, time crystals trap quantum correlations in repeating loops, creating a toy model for how gravity might encode information, a potential clue to the black hole information paradox. Yet the wildest prospect lies in time crystals' relationship with causality. Normally, time's arrow points rigidly forward, but these structures blur that directionality, exhibiting correlations between states that don't neatly follow cause and effect. Some physicists speculate that studying them could reveal how time's flow emerges from timeless quantum laws, or even how to engineer systems where time's arrow becomes malleable. While no one's building a time machine yet, time crystals hint that gravity's grip on time might be more flexible than Einstein ever imagined. From quantum computers exploiting their stability to simulations of cosmic phenomena, time crystals are more than lab oddities, they're proving grounds for the universe's deepest secrets. Every oscillation carries a message. Time might not be the smooth, continuous river we perceive, but something far stranger, a cascade of crystalline moments, each shaped by gravity's invisible hand. And as experiments grow more sophisticated, these elusive structures may yet crack open the door to a theory of quantum gravity, revealing how time itself is woven into the cosmos's foundation. Every moment that passes feels like an unstoppable march. Eggs don't unscramble, coffee never unstains your shirt, and you can't unburn toast. This relentless forward motion is what physicists call the arrow of time, and while chaos and entropy play their part, gravity is the silent conductor orchestrating time's one-way symphony. Think of the universe as a deck of cards scattered across a table. Entropy explains why the cards won't spontaneously rearrange into a neat stack, but gravity is what pulled them into a messy pile in the first place. Without gravity's relentless pull, there'd be no galaxies, no stars, no planets, just a thin, uniform haze of particles drifting endlessly. It's gravity that transformed the smooth soup of the early universe into the clumpy cosmic web we see today, and in doing so, it gave time its direction. Consider the Big Bang. In those first moments, the universe was a searing, nearly uniform plasma. But tiny quantum fluctuations, random blips in density, gave gravity something to work with. Over billions of years, gravity amplified those imperfections, drawing matter into dense knots that became galaxies, while the space between them stretched into vast voids. This process didn't just shape the cosmos, it set time's arrow in motion. As matter clumped, stars ignited, forging heavier elements and creating the conditions for complexity, planets, life, even consciousness. Without gravity's organizing power, the universe would have remained a featureless fog, and time would have no story to tell. Yet gravity's influence on time isn't just historical. It's still at work today, shaping the universe's expansion. Dark energy may be pushing galaxies apart, but gravity fights back, pulling clusters together in a cosmic tug of war. This struggle doesn't just determine whether the universe will end in a big crunch or a big rip, it influences how time itself flows on the grandest scales. In regions where gravity dominates, like galaxy clusters, time slows relative to emptier voids. It's as if the universe has countless time zones, each ticking at its own pace, all governed by gravity's invisible hand. The real mystery lies in whether time's arrow is fundamental or just a side effect. Some theories suggest time might emerge from the way gravity entangles quantum particles, like a movie projected from a reel of static frames. Others propose that in a multiverse, different regions could have arrows pointing in opposite directions, with gravity dictating which way time flows in each pocket. Even black holes complicate the picture. Their singularities might be places where time's arrow breaks entirely, looping back on itself in ways that defy our intuition. What's clear is that gravity doesn't just bend space-time, it gives time its purpose. Without it, the universe would be a static, timeless void. But thanks to gravity's relentless pull, we have a cosmos where things change, evolve, and remember. From the birth of stars to the ticking of clocks, gravity's grip on time is the reason there's a past to study and a future to imagine. And as we peer deeper into black holes, simulate quantum gravity, and map the universe's expansion, we're not just uncovering how time works, we're learning why it moves forward at all. Light doesn't always travel in a straight line. Sometimes it takes the scenic route. When a beam of light passes near a massive galaxy or galaxy cluster, gravity tugs at it like an invisible hand, bending its path and slowing its journey in a phenomenon called gravitational lensing. But here's the twist: this cosmic detour isn't just a spatial illusion. It's a time delay baked into the fabric of reality. The light doesn't just curve, it lags, arriving later than it would in a gravity-free universe. This subtle slowdown, known as the Shapiro time delay, is one of relativity's most precise predictions, and a stunning reminder that gravity doesn't just warp space, it stretches time itself. The mechanics are deceptively simple. Picture a photon racing toward Earth from a distant quasar billions of light years away. If its path skirts the edge of a massive galaxy, spacetime's curvature forces the light to travel a slightly longer distance. But because gravity also slows time near massive objects, the photon's journey isn't just extended, it's also dragged out, as if the light is moving through cosmic molasses. The result, a measurable delay, sometimes by mere milliseconds, other times by days or even years, depending on the mass of the intervening object. It's as if the universe itself is putting traffic cones on light's highway, forcing it to take the slow lane. Astronomers exploit this effect like cosmic stopwatches by comparing light from lensed objects with light that traveled unobstructed. They can map gravity's fingerprint on time across unfathomable distances. One of the most famous tests came in the 1970s when scientists bounced radar signals off Venus and Mercury as they passed behind the Sun. The signals that grazed the Sun's gravitational field arrived slightly later than expected, just as Einstein's equations predicted. Today, we see this play out on galactic scales. When a supernova's light is lensed by a foreground galaxy, multiple images of the explosion appear around the galaxy's edges, each arriving at different times due to the varying paths and gravitational delays. These time-lapse supernovas let astronomers triangulate the mass of the lensing galaxy with precision, weighing invisible dark matter in the process. But the real magic happens when lensing reveals the unseen. In 2018, astronomers observed a distant star brighten and fade multiple times over weeks, a signature of light being lensed by an invisible object. The culprit, a rogue black hole or neutron star drifting undetected through space, betrayed only by its gravitational grip on time. Similarly, when the quasar Q0957 plus 561 was first found to produce twin images in the 1970s, the time delay between them, 417 days, allowed scientists to calculate the mass of the lensing galaxy cluster with unprecedented accuracy, including its halo of dark matter. Gravitational lensing isn't just a tool for measuring mass. It's a window into gravity's most subtle choreography. The delays encode information about the lens's structure, the expansion rate of the universe, even the nature of space-time itself. Some theorists speculate that if exotic objects like cosmic strings, infinitely thin wrinkles in space-time exist, their lensing signatures would include bizarre time delays unlike anything produced by ordinary matter. Others use lensing time delays to test whether gravity's constants have drifted over cosmic history, probing for cracks in relativity's foundation. What makes this phenomenon so extraordinary is how it marries the cosmic and the quantum. On one hand, it's a large-scale testament to gravity's power, light bending around galaxies like a car around a roundabout. On the other, the delays are so exquisitely sensitive that they could one day reveal quantum fluctuations in spacetime itself if we learn to measure finely enough. Every lensed image, every delayed photon, is a message from the universe. Gravity doesn't just tell matter how to move, it tells time how to flow. And as telescopes grow sharper and algorithms more sophisticated, these subtle delays may yet unveil secrets about dark energy, extra dimensions, or the very nature of time's arrow. For now, they stand as silent proof that even light, the fastest thing in the universe, can't escape gravity's patient grasp. Our universe operates under a strict set of physical laws. Gravity pulls, time marches forward, and matter behaves predictably. But what if ours isn't the only possible configuration? The multiverse hypothesis suggests countless alternate realities might exist, each with its own unique physics. In some, gravity could be repulsive instead of attractive, flinging planets apart rather than holding them together. In others, time might flow backward or in chaotic loops, with effects preceding causes in a topsy-turvy reversal of reality. These aren't just thought experiments, they're serious challenges to our deepest assumptions about how gravity and time must behave. Take the idea of a universe where gravity weakens over distance instead of strengthening. Stars in such a cosmos wouldn't orbit, they'd drift aimlessly, never clumping into galaxies. time might lack any consistent direction, with entropy decreasing randomly instead of increasing. Some theories even propose universes with extra-spatial dimensions, where gravity could leak between realms, causing time to stutter unpredictably like a glitching video. The bizarre part, these alternate physics aren't mathematically impossible. They're solutions to the same equations that describe our own universe, just with different starting conditions. The real test comes when we ask how time would function in these exotic realms. Imagine a universe where gravity's strength depends on an object's temperature instead of its mass. Hot stars might bend time into pretzels, while cold planets experience it linearly. Or consider a hypothetical, anti-de Sitter universe, where gravity is so intense at large scales that time becomes cyclical every Big Bang, eventually leading to a big crunch, resetting the cosmic clock over and over. These scenarios aren't just whimsical. They're tools physicists use to stress test whether our laws of gravity are truly universal or just local bylaws in a grander cosmic metropolis. Some of the wildest possibilities emerge from string theory, which suggests our universe might be a three-dimensional brane floating in higher dimensional space. In such models, gravity could behave radically differently in nearby branes. Perhaps time flows faster in some, slower in others, or even in multiple directions simultaneously. Collisions between branes might create temporary pockets where gravity briefly shuts off, freezing time entirely before snapping back to normal. While purely theoretical, these ideas force us to confront whether gravity's grip on time is a fundamental truth or just an accident of our particular cosmic address. The hunt for evidence is already underway. If alternate universes with different gravity exist, they might leave faint imprints on our cosmic microwave background, like shadows of a neighboring reality's gravity warping our own. Others speculate that certain patterns in quantum fluctuations could betray gravity's behavior in other dimensions. Even more radically, some physicists propose that dark energy, the mysterious force accelerating our universe's expansion, might actually be gravity leaking from a parallel universe, subtly altering time's flow here without us realizing. What makes these ideas so compelling isn't just their strangeness, but what they reveal about our own reality. By imagining universes where gravity and time obey different rules, we better understand why ours works the way it does. Perhaps gravity's constancy isn't a law, but a consequence of deeper principles, like how ice always melts at the same temperature under Earth's pressure, but might behave differently on a neutron star. The multiverse, in all its speculative glory, holds up a mirror to our physics, showing us which aspects are flexible and which might truly be universal. Until we find proof or disprove them, these alternate realities will keep stretching our notions of what gravity can do to time and how deeply the two are intertwined. Artificial gravity is one of science fiction's most enduring tropes, spinning space stations in 2001, A Space Odyssey, magnetic boots in the expanse, or warp drives bending space-time in Star Trek. But what if the secret to mimicking gravity isn't just about keeping astronauts' feet on the floor? What if it could unlock the ability to tweak time itself? The quest to engineer gravity isn't just about comfort in space. It's a gateway to probing one of Einstein's most radical ideas, that gravity and time are two sides of the same cosmic coin. Right now, the closest we've come to artificial gravity is brute force simulation, spinning a spacecraft like a carnival ride to create centrifugal force. The International Space Station has toyed with this idea, but the sheer size needed for comfortable rotation makes it impractical yet. But imagine a future where we don't just spin habitats, but manipulate inertia itself. Some theories suggest that if we could generate powerful enough gravitational fields, perhaps using dense, rotating masses, or even hypothetical materials like negative energy, we might replicate gravity's time-bending effects. Picture a lab where scientists dial up artificial gravity in a chamber and clocks inside start ticking slower compared to those outside. It sounds like fantasy, but the physics doesn't forbid it. Even wilder are experiments with superconductors and magnetic fields. When certain materials are cooled to extreme temperatures, they expel magnetic fields in a way that mimics gravitational effects. In labs, scientists have levitated objects using this phenomenon, called the Meissner effect. Some researchers speculate that under the right conditions, these fields could create localized distortions in space-time, microscopic versions of the warps caused by planets or stars. If we could scale this up, could we engineer not just artificial gravity, but artificial time zones? A room where time flows at 90% speed could revolutionize everything from computing to space travel, letting us store time like energy in a battery. The real breakthrough would come if we could harness spacetime's flexibility directly. Theories like Alcubierre's warp drive propose bending spacetime itself to move faster than light, a concept that, while speculative, isn't ruled out by relativity. If we could compress space-time ahead of a ship and expand it behind, we wouldn't just be creating gravity, we'd be sculpting time's flow around the vessel. Astronauts might experience a 2-year journey while decades pass on Earth, effectively time traveling into the future. The catch: it would require exotic matter with negative energy, something we've never observed. But the fact that it's mathematically possible keeps the dream alive. Of course, the implications go far beyond engineering. If we could control gravity, even in small ways, we'd be testing the limits of general relativity itself. Does artificial gravity warp time exactly like natural gravity? Could we create time lenses that focus or diffuse time's passage like glass bends light? The answers might redefine everything from quantum computing, where precise timing is crucial, to cosmology, where understanding gravity's grip on time could reveal hidden layers of the universe's structure. For now, the best glimpses of artificial gravity's potential come from particle accelerators and space-based experiments. When protons are whipped to near light speeds in the Large Hadron Collider, time dilation makes their decay rate slow dramatically from our perspective. It's a fleeting, microscopic hint of what might be possible if we could stabilize and control such effects. Meanwhile, plans for rotating lunar habitats or Mars bases could provide real-world data on how simulated gravity affects biology, and whether time's flow for a colonist in a spinning pod differs measurably from someone on Earth. The dream isn't just about dodging bone loss in space, it's about tapping into gravity's deepest secret, its dominion over time. Every experiment, from spinning centrifuges to quantum levitation, brings us closer to answering whether time's tempo is something we can one day compose ourselves. And if that day comes, the line between science fiction and reality won't just blur, it might bend, twist, or even loop back on itself. Gravity batteries might sound like something out of a steampunk novel, but they're one of the most elegant examples of how gravity's grip on time translates into real-world engineering. Imagine a massive weight suspended high above the ground, say, a 30-ton block of concrete hoisted by cranes inside a disused mine shaft. When the power grid has excess electricity, maybe from a surge of solar energy on a sunny afternoon, that energy isn't wasted. Instead, it's used to lift the weight, converting electrical energy into gravitational potential energy. Then, when demand spikes in the evening, the weight is lowered, its slow descent turning generators to release the stored energy back into the grid. It's a simple concept, but the brilliance lies in how it mirrors gravity's cosmic role as the universe's ultimate timekeeper. What makes this more than just mechanical energy storage is the way it plays with time's flexibility. On a cosmic scale, gravity dictates how time flows, slowing it near massive objects, speeding it up in voids. A gravity battery does something similar on a human scale. It takes energy produced at one moment in time and holds it in suspension, literally banking it for later use. The weight poised at height is like a frozen moment of potential, a physical manifestation of energy paused in time until gravity is allowed to reclaim it. This isn't just storage, it's temporal engineering, leveraging gravity's fundamental relationship with time to solve a practical problem. The parallels go deeper. Just as a black hole's immense gravity stretches time to a near standstill from an outsider's perspective, a gravity battery exploits the tension between height and time. The higher the weight is lifted, the more energy it stores, not just because of the increased distance, but because gravity's pull weakens slightly with altitude, introducing a tiny but measurable time dilation effect. Over the scale of a mine shaft, this is negligible, but the principle is the same one that governs atomic clocks on GPS satellites. In both cases, gravity's influence on time isn't just theoretical, it's harnessed. Pilot projects are already proving the concept's viability. In Switzerland, a company has repurposed an abandoned railway tunnel to test a gravity battery system using massive robotic cranes and stacked concrete blocks. In the Nevada desert, another startup is designing a tower where weights are hoisted and lowered autonomously, acting like a giant mechanical battery. Even abandoned oil wells are being eyed as potential sites, with weights dropped deep into the Earth's crust, where gravity's pull is marginally stronger, adding another layer of efficiency. These systems aren't just cheap and scalable, they're also incredibly durable, with lifespans measured in decades, unlike chemical batteries that degrade over time. The beauty of gravity batteries lies in their universality. They require no rare earth metals, no toxic chemicals, just mass and height, two things Earth has in abundance. And unlike pumped hydro storage, which relies on specific geography, gravity batteries can be built anywhere there's vertical space. But the most poetic aspect is how they echo gravity's grandest cosmic functions. Just as a star's gravity traps light in its orbit, or a planet's mass bends the path of time, these batteries trap energy in gravity's grip, releasing it precisely when needed. They're a reminder that the same force that shapes galaxies can also help power our homes, and that time, in the end, is just another resource waiting to be harnessed. Time might feel like the most fundamental part of reality, an ever-flowing river we're all swept along in. But what if time isn't foundational at all? What if it's more like a side effect, an illusion conjured up by something deeper? That's the radical idea some physicists are wrestling with, that time didn't exist before gravity, but emerged alongside it in the fiery aftermath of the Big Bang. Picture the universe's birth not as an explosion in time, but as the moment time itself flickered into being, woven into existence by gravity's first pull. This isn't just philosophical musing, it's a concrete prediction of loop quantum gravity, one of the leading theories attempting to unite Einstein's relativity with quantum mechanics. In this framework, spacetime isn't smooth and continuous but built from tiny, indivisible threads like a cosmic tapestry. Gravity arises from the way these threads intertwine, and Time might simply be the way we perceive changes in this woven structure. Think of it like watching a movie. What feels like continuous motion is actually a series of still frames flashing by. Similarly, our experience of time's flow could be the brain stitching together discrete jumps in spacetime's underlying fabric. The implications are staggering. If time is emergent rather than fundamental, it means the universe could have existed in a timeless state before gravity took hold, Some models of the pre-Big Bang cosmos describe it as a quantum foam, a seething, chaotic realm where causality breaks down and events don't happen in any particular order. Only when gravity condensed this foam into something structured did time as we know it crystallize, like ice forming from turbulent water. This would mean the Big Bang wasn't just the birth of matter and energy, but the moment gravity forged time's arrow, setting the cosmic clock ticking. Clues to this mystery might lie in black holes. At a singularity, both time and gravity reach their extremes, crushing our known physics into oblivion. Some theorists suggest that if you could peer beyond the event horizon where time effectively freezes from an outsider's perspective, you might catch glimpses of a realm where time unravels back into its pre-gravity state. It's as if black holes aren't just cosmic dead ends, but windows into time's primordial origins. Even more provocative are hints from quantum mechanics. At microscopic scales, particles don't behave as if they're moving through time at all. Entanglement, the eerie link between particles that defies distance, seems to operate outside time's usual constraints. This has led some researchers to propose that time might be a collective hallucination, a useful fiction that large objects like humans experience because gravity averages out quantum weirdness. In this view, gravity isn't just another force, it's the stage manager of reality, directing when and how time appears in the cosmic play. The stakes couldn't be higher. If time is truly a byproduct of gravity, it rewrites our understanding of the universe's birth. No longer would we ask, what happened before the Big Bang? But rather, how did time emerge from timelessness? It also raises spine-tingling questions about time's end. Could a universe where dark energy rips space-time apart ultimately see time dissolve back into chaos? Or might gravity find a way to reweave time's fabric anew? For now, experiments are inching us closer to answers. Quantum gravity detectors are hunting for spacetime's hypothesized granularity, while simulations of the early universe explore how time might have crystallized from chaos. Every new piece of data is a potential clue, a flicker of insight into whether time is the canvas of reality, or just one of gravity's most mesmerizing creations. One thing's certain, if time is indeed gravity's invention, then every tick of the clock is a silent testament to its power. String theory rewrites the cosmic rulebook by proposing that our universe isn't just the three dimensions of space and one of time we experience. It's a shadow cast by deeper, higher dimensional realities. Imagine living on the surface of a pond, unaware of the underwater currents shaping the ripples above. In this view, gravity's strange grip on time might not be fundamental at all, but a side effect of forces playing out in dimensions we can't see. Some models suggest that what we perceive as time could be like the second hand on a clock, merely tracking deeper, timeless mechanics unfolding in realms with 5, 10, or even 26 spatial dimensions. Take the holographic principle, one of string theory's most mind-bending offshoots. It proposes that our four-dimensional spacetime might be a projection from a two-dimensional surface at the universe's edge, like a cosmic Instagram filter translating higher dimensional physics into a format our brains can process. In this scenario, gravity's time warping effects could be artifacts of how information gets rendered into our reality. A black hole's event horizon where time seems to freeze might not be where time slows down, but where the projection falters, like a glitch in the matrix revealing the higher dimensional code beneath. The real kicker, if time emerges from these hidden layers, it might not flow at all in the ultimate reality. Physics equations work equally well backward or forward in time, leading some theorists to argue that our experience of time's arrow is like a movie reel, individual frames, timeless quantum states that only appear continuous when viewed in sequence. Gravity's role could be akin to the projector's mechanism, creating the illusion of motion by stitching these snapshots together. This would mean that when we measure time dilation near a planet or star, we're not seeing time itself bend, but observing how gravity alters the frame rate of reality's projection. Experimental clues are tantalizing but elusive. If extra dimensions exist, gravity might leak into them, explaining why it's so weak compared to other forces. The Large Hadron Collider has hunted for microscopic black holes that could form if higher dimensional gravity were strong enough at tiny scales, though none have appeared yet. More subtly, precise measurements of gravitational waves might one day reveal faint echoes of collisions not just in our dimensions, but in others, like hearing a conversation through a wall. Yet the most profound implication is philosophical. If time is emergent rather than fundamental, it reshapes how we think about existence itself. The Big Bang might not be the beginning of time, but the moment our slice of reality booted up from timeless higher dimensional data. Even consciousness, our subjective flow of moments, could be a clever hack of the brain, interpreting dimensional shifts as the passage of time. Gravity, then, isn't just bending time. It might be the loom weaving the illusion of time's fabric altogether. Until we crack the code of higher dimensions, we're like flatlanders puzzling over shadows, unaware of the richer reality casting them. Every collision, every cosmic cataclysm leaves scars, not just on the objects involved, but on the fabric of space-time itself. Imagine dropping a stone into a pond. The ripples fade, but the water retains a subtle memory of the disturbance in its molecular motion. Now scale that up to the universe. When black holes merge or neutron stars collide, the gravitational waves they emit don't just vanish into the void. According to cutting-edge theories, space-time might remember these events through permanent distortions called gravitational memory, an imprint as real as a fingerprint on glass, but etched into the geometry of reality. This phenomenon isn't just theoretical poetry. When LIGO detects gravitational waves from distant collisions, the detectors don't snap back to their original state like a rubber band. They're left ever so slightly displaced, as if spacetime itself has been stretched taut by the passing ripple. These nanometer-scale shifts are the smoking gun for gravitational memory, proof that spacetime doesn't just bend. It retains a ghostly afterimage of the violence that warped it. It's as if the universe keeps a ledger of every major gravitational event, written in a language of strain and curvature we're only beginning to decipher. The implications rewrite our understanding of information in the cosmos. Black holes were long thought to be ultimate shredders, swallowing matter and erasing its information, a paradox that troubled even Einstein. But gravitational memory suggests a loophole. When matter falls into a black hole, it might not vanish without a trace. Instead, its gravitational fingerprint could linger on the event horizon, encoded in the space-time deformations it leaves behind. This would mean black holes don't destroy information. They transform it into gravitational tattoos hidden in plain sight. Future detectors, like the space-based LISA Observatory, could hunt for these imprints in the afterglow of mergers, piecing together what fell into the cosmic abyss billions of years ago. Even more tantalizing is how gravitational memory might reveal time's arrow on cosmic scales. Normally, physics equations work equally well backward or forward. There's no mathematical reason time must flow in one direction. But gravitational memory is different. It's inherently one way. Just as you can't unring a bell, you can't erase space-time's memory of a passing gravitational wave. This irreversible quality makes it a prime candidate for explaining why the universe remembers the past but not the future. Some theorists speculate that the sum of all gravitational memories since the Big Bang could be what gives time its direction, like footprints in cosmic sand showing which way the wind blew. The hunt for these imprints is already underway. By analyzing data from LIGO and Virgo, scientists are looking for telltale offsets in detector mirrors that persist long after the gravitational waves pass. Other proposals suggest studying pulsars rapidly spinning neutron stars that act as cosmic lighthouses. If a gravitational wave with memory alters the spacetime between us and a pulsar, its pulses should arrive slightly earlier or later forever after, a permanent timestamp of the disturbance. These methods aren't just about confirming a quirky prediction, they're probes into whether spacetime is fundamentally sticky, preserving a history of its own deformation. What's at stake goes beyond astrophysics. If gravitational memory is real, it implies that spacetime is more than a passive stage. It's an active participant in the universe's unfolding story, recording events like a cosmic DVR. This could revolutionize how we think about quantum gravity, black hole thermodynamics, even the nature of time itself. Every ripple in spacetime's fabric might carry not just energy but information, a whisper from the past that never fully fades. And as detectors grow more sensitive, we may find that the universe's history isn't written in stars or galaxies alone, but in the silent, stretching memory of spacetime itself. Time travel isn't just the stuff of science fiction, it's hidden in the fine print of Einstein's equations. General relativity allows for the existence of closed time-like curves, paths through spacetime that loop back on themselves like a Möbius strip of reality. Picture a hiker walking in circles around a mountain, returning to their starting point, except in this case, the mountain is gravity so intense it twists time into a knot, and the hiker arrives not just where they began, but when they began. This isn't a paradox waiting to happen. It's a mathematical possibility woven into the fabric of the universe, courtesy of gravity's dominion over time. The most famous blueprint for a time machine involves wormhole shortcuts through spacetime predicted by relativity. Imagine folding a piece of paper so two distant points touch, then punching a hole through them. In theory, a wormhole could connect not just places but moments. Step in one end on Earth in 2050, and you might emerge near a distant star in 2024. But here's the catch: wormholes are inherently unstable. They'd snap shut instantly unless propped open by exotic matter, hypothetical stuff with negative energy that repels gravity rather than attracts it. No such material has ever been found, but quantum physics whispers that it might exist in fleeting, microscopic quantities. If we could somehow harvest and stabilize it, a wormhole time machine might not be impossible, just improbably difficult. Another cosmic oddity that could bend time into loops is the spinning cosmic string, infinitely thin filaments of energy left over from the Big Bang, thinner than an atom but denser than a neutron star. If two such strings moved past each other at near light speed, their immense gravity would warp spacetime so severely that closed time-like curves would form around them. Fly a spaceship in just the right path around these strings, and you could emerge before you left. The strings themselves might be undetectable, but their gravitational lensing effects could betray their presence. Some astronomers have even scoured old galaxy surveys for strange, straight-line gravitational lenses, possible cosmic strings hiding in plain sight. Of course, time travel comes with headaches even physics can't cure. The grandfather paradox, where a time traveler prevents their own birth, is just the start. Quantum mechanics offers a possible workaround. The multiverse theory suggests that tampering with the past might spawn a parallel timeline, leaving the original history untouched. But general relativity remains stubbornly silent on whether nature would allow such loopholes. Even if closed time-like curves exist, the universe might enforce a no free lunch policy, where quantum effects conspire to prevent paradoxes, perhaps by collapsing wormholes the moment a time traveler tries to change the past. What's fascinating isn't just the theoretical possibility, but how seriously physicists take it. Kip Thorne, the Nobel laureate who advised on Interstellar, has published papers on wormhole time machines. Stephen Hawking once proposed the chronology protection conjecture, a tongue-in-cheek suggestion that the laws of physics might actively prevent time travel to keep history tidy. Yet to date, no one's found a fundamental rule that forbids it, just engineering challenges of cosmic proportions. The deeper lesson here isn't about building DeLoreans, but about gravity's role as the ultimate architect of time. Whether through wormholes, cosmic strings, or some yet undiscovered phenomenon, gravity doesn't just bend space-time, it can potentially fold it into origami. These ideas stretch our understanding of cause and effect, challenging us to rethink how time's arrow is tethered to the universe's structure. For now, time travel remains a thought experiment, but in a universe where gravity writes the rules, even the wildest dreams might have roots in reality. Gravity shapes planets, bends light, and warps time, but could it also shape the very fabric of our thoughts? At the crossroads of neuroscience and quantum physics, a provocative idea lingers that gravity's subtle dance with time might play a role in consciousness itself. It sounds like the plot of a sci-fi novel, but a handful of scientists argue that the brain could be sensitive to spacetime's minute fluctuations, turning gravity into an invisible puppeteer of perception. Consider how we experience time. A minute stuck in traffic feels endless, while an hour with friends flies by. Our brains already distort time's flow based on context, but what if gravity's influence goes deeper? In the 1980s, physicist Roger Penrose proposed that quantum processes in neurons, specifically inside structures called microtubules, might interact with spacetime's geometry. His controversial theory, orchestrated objective reduction, suggests that consciousness arises when these quantum states collapse under gravity's pull, like sandcastles dissolving under a tide. While mainstream neuroscience remains skeptical, the idea challenges us to ask, could the gravitational tugs of the moon or even distant planets subtly alter how we perceive moments? The implications spiral into philosophy. If gravity molds time and time perception is linked to consciousness, then our sense of self might be entangled with the cosmos in ways we've barely imagined. Ancient cultures tracked celestial cycles to mark rituals. Could there have been an intuitive grasp of gravity's psychological whispers? Modern experiments hint at strange connections. Atomic clocks placed at different elevations confirm time's malleability, so why not the brain's electrochemical rhythms? Even Earth's gravity isn't uniform. Tiny variations exist between mountains and valleys, cities and deserts. Could lifelong exposure to these differences nudge cognition, like living at high altitude alters physiology? Critics dismiss these speculations as wishful thinking, pointing out that gravity's effects at the scale of neurons are astronomically small. Yet nature often exploits subtle forces in unexpected ways. Monarch butterflies navigate using quantum effects in their eyes, and birds sense Earth's magnetic field through cryptochrome proteins. If biology can harness quantum mechanics for migration, why not gravity for time perception? The brain's 86 billion neurons fire in precise synchrony, a symphony where even picosecond delays could scramble meaning. Perhaps gravity's time bending, faint as it is, helps tune that orchestra. The debate touches existential questions. Is consciousness a purely local phenomenon, or does it ripple through space-time like gravity itself? Could disorders like depression or schizophrenia, which distort time perception, involve gravitational sensitivities we don't yet understand? The theories remain fringe, but their boldness pushes science to explore the unknown. After all, electromagnetism once seemed separate from life, until we discovered it powers every heartbeat and thought. Gravity, the universe's quietest force, might yet have secrets to share about the mind's deepest workings. For now, the link between gravity and consciousness is a canvas for speculation, painted with equal parts inspiration and skepticism. But in a universe where time bends and matter warps space, dismissing the idea outright might be the least scientific stance of all. Whether future research vindicates or refutes these theories, one truth endures: gravity's reach extends far beyond the cosmos into the very way we experience being alive. Atomic clocks aboard the International Space Station are ticking in a silent race against their Earth-bound twins, not to keep better time, but to lose it. These ultra-precise timepieces, chilled to near absolute zero and measuring the vibrations of atoms, are humanity's most sensitive tools for catching gravity red-handed in the act of warping time. As they orbit 250 miles above Earth, where gravity is marginally weaker, the clocks gain about 45 microseconds per year compared to their counterparts on the ground. That tiny difference, smaller than the blink of an eye, is a monumental victory for Einstein, proving his theory right down to the thousandth of a decimal. But scientists aren't just celebrating, they're pushing further. The next generation of space clocks, like NASA's Deep Space Atomic Clock, aims to measure time dilation with 50 times more precision, hunting for deviations that could hint at physics beyond Einstein's imagination. Meanwhile, on the Moon, a retroreflective experiment left by Apollo astronauts is revealing gravity's grip on time across celestial distances. For 50 years, scientists have been firing lasers at these mirrored panels and timing how long the light takes to bounce back. The results: the Moon is drifting away at nearly 4 centimeters per year, but buried in the data is something even stranger. The laser pulses slow measurably as they pass through Earth's gravitational field, a delay that matches relativity's predictions to within a hair's breadth. This lunar laser ranging isn't just measuring distance, it's a galactic-scale stopwatch, proving that even over 240,000 miles, gravity leaves its mark on time's flow. Back on Earth, the alpine peaks of the Matterhorn have become an unlikely laboratory for gravity's subtleties. Physicists recently hauled atomic clocks to its summit and base camp, comparing their ticks across just a few thousand feet of elevation. The higher clocks ran faster, as expected, but the team also detected minute discrepancies linked to the mountain's mass-bending spacetime beneath them. It's a reminder that gravity's time twisting isn't just about altitude. It's about the density of the rock beneath your feet, the shape of the terrain, even the pull of underground magma chambers. These experiments are turning entire landscapes into gravity detectors, revealing how local geology sculpts time's passage in ways GPS satellites must account for. The most audacious test of all might be the upcoming satellite mission STQuest, designed to compare clocks separated by thousands of miles with unprecedented accuracy. By linking atomic clocks in space and on Earth with quantum-entangled photons particles that remain mysteriously connected across any distance, the experiment could detect space-time ripples from passing gravitational waves or even anomalies suggesting extra dimensions. It's not just about confirming relativity, it's about probing the fringes of known physics where gravity might start behaving oddly. What ties these experiments together is a single, profound question. Does gravity's effect on time hold perfectly at every scale? Or will we someday find a crack in Einstein's equations? The answer could rewrite everything from how we navigate to the fate of the universe. Every tick of these hyper-precise clocks is a heartbeat of discovery, measuring not just time but the very fabric of reality. The next decade of gravity research is poised to crack open cosmic mysteries we've barely begun to imagine. At the forefront is LISA, the Laser Interferometer Space Antenna, a revolutionary mission set to launch in the 2030s. Unlike Earth-bound detectors like LIGO, which catch high-pitched chirps from stellar mass black holes, LISA-3 spacecraft will form a triangular observatory 2.5 million kilometers per side, floating in deep space. This colossal scale lets it tune into the universe's deepest base notes, the mergers of supermassive black holes, events so powerful they warp spacetime for years. Imagine hearing the collision of billion sun behemoths that shook the cosmos when galaxies were young, a sound so low it vibrates once every few hours, dragging time itself forward and backward like a slow-motion tidal wave. These signals won't just reveal how black holes grow, they'll test whether gravity behaves differently in extreme regimes, potentially exposing cracks in Einstein's framework. But LISA is just one instrument in an expanding symphony of next-generation tools. Here on Earth, quantum sensors are achieving freakish precision, measuring minuscule gravity-induced time shifts across distances shorter than a human hair. These devices exploit quantum entanglement, the eerie link between particles, to detect spacetime's hypothetical granularity. If spacetime is pixelated at the Planck scale, as some quantum gravity theories suggest, these sensors might catch gravity stuttering as it interacts with matter, like a vinyl record skipping on cosmic static. Already, prototypes have measured Earth's gravitational pull with such sensitivity they could track underground water reservoirs or magma movements, turning the planet itself into a laboratory for fundamental physics. Meanwhile, the James Webb Space Telescope's successors, like the proposed Habitable Worlds Observatory, will peer at galaxies so ancient their light was emitted when gravity's grip on time might have differed subtly. By analyzing quasars whose light bent around foreground galaxies billions of years ago, astronomers could detect whether the strength of gravity has drifted over cosmic epochs. Even tabletop experiments are joining the fray, with some teams levitating microdiamonds in vacuum chambers to probe whether gravity operates the same at microscopic scales. The haunting question driving all this: is gravity truly universal, or does it have hidden preferences, stronger here, weaker there, that rewrite time's rules across the cosmos? The most radical breakthroughs may come from combining these approaches. Picture LISA spotting a supermassive black hole merger while neutrino observatories catch particles emitted by the event's aftermath, and next-gen telescopes record the accompanying flash. This multi-messenger astronomy could reveal whether gravitational waves arrive in lockstep with light, or if they lag, hinting at extra dimensions where gravity leaks. Other projects, like the Einstein telescope, aim to build underground detectors so quiet they'll hear gravitational waves from the universe's first seconds, potentially uncovering phases when time itself might have crystallized from a pre-geometric chaos. What's at stake isn't just academic. If spacetime has hidden layers, or if gravity's constants aren't so constant, it could reshape everything from quantum computing to interstellar travel. Atomic clocks precise enough to detect a black hole's gravitational whispers might also enable GPS that never drifts, even on Mars. Understanding gravity's quantum quirks could unlock propulsion that warps spacetime intentionally, nudging humanity toward the stars. And if we confirm that time's flow is truly malleable, not just near black holes but in labs, it might force us to rethink causality itself. What it means to be before, after, or simultaneous in a universe where gravity calls the shots. The coming years will test whether gravity is the universe's steadfast stagehand or a capricious director, changing time's script when we're not looking. With each new experiment, we're not just observers of this drama, we're participants, shaping the questions as much as seeking answers. And somewhere in the data, between the faintest quantum tremor and the loudest space-time quake, lies the possibility that gravity's next act will rewrite everything we thought we knew about time's rhythm. From mountain peaks to black hole edges, gravity's silent manipulation of time is a testament to the universe's profound interconnectedness. Think about the last time you checked your phone for the time. Those digits ticking forward aren't just tracking moments, they're revealing gravity's hidden signature. The same force that keeps your feet planted on the ground is also stretching and compressing time itself, like an invisible hand tuning the cosmos's metronome. We've traveled from Einstein's aha moment, realizing gravity warps spacetime like a trampoline sagging under a bowling ball, to the cutting edge of quantum experiments where scientists probe whether time itself might emerge from something deeper. Every discovery peels back another layer of spacetime's secrets, those atomic clocks on the International Space Station, forever gaining microseconds against Earth-bound twins. They're not just scientific curiosities, they're proof that gravity's time-bending effects touch even our most mundane technologies. The GPS guiding your road trip, the lasers bouncing off the moon's surface, even the strange behavior of particles inside black holes, all whisper the same truth. Time is fluid, personal, and utterly at gravity's mercy. Yet the most thrilling part isn't what we've learned, it's what remains just beyond our grasp. Could gravity's rules change in the vacuum of deep space or the heart of a neutron star? Might dark matter's invisible pull be warping time in ways we haven't yet detected? The next generation of experiments, space-based gravitational wave observatories, quantum sensors buried underground, telescopes peering at the universe's first light, will push our understanding further, perhaps revealing that gravity's grip on time is even stranger than Einstein imagined. So the next time you glance at a clock, take a beat to marvel at the cosmic forces behind that simple tick. Your seconds here on Earth pass differently than an astronaut's in orbit or a photon's near a black hole. Gravity isn't just shaping the universe, it's composing time's symphony, one warped note at a time. If this journey through spacetime's twists and turns sparked your imagination, drop a comment below what fascinates you most about gravity's hidden role in time. And remember, whether you're scaling a mountain or lounging at sea level, you're not just living in time, you're surfing its gravity-bent waves. Until our next cosmic adventure, stay curious and keep your eyes on the sky.